Welcome all. So, we will be continuing our study of the ductile behavior of the materials. Okay. So, today we will be looking into the fatigue and cyclic loading. Okay. So, though fatigue and cyclic loading is not very much apparent during the dynamic loading. So, we will just give a very quick review of the fatigue loading. Okay. So, the fatigue loading, what happens in a fatigue loading? So, in a fatigue loading the failure is caused by the repeated application of the different stress cycle. Okay. And interestingly what happens is that during a fatigue type of loading, okay, the fracture will occur well below the yield strength. Okay. So, this phenomena accounts for the 90% of all failures in the metallic component. Okay. During the service conditions, when the system is undergoing repeated fatigue loading, okay, the system will fail at a value which is much lower than the yield strength. Okay. So, in the dynamic aspects, okay, what can happen? Okay. So, if there is a high frequency loading, okay, it can cause local heating and this will alter the material properties. This dynamic loading, okay, with high frequency loading, they can cause the fracture initiation or the crack initiation, and it often starts at the surface defects or stress concentrations. Okay. And this crack will keep on increasing. Okay. The rate of this crack growth will keep on increasing with the increasing loading amplitude and frequency. Okay. So, if we are using rotating machinery parts, okay, or an aerospace structures, bridge loading which undergoes repeated cycle of fatigue loading and some sort of automotive parts. Okay. So, during this type of fatigue loading the failure occurs. Okay. So, this is what is known as an Ascent curve. Okay. So, here is the number of cycles in the x axis, it is denoted by number of cycles, and y is a log cycle which denotes the stress. Okay. So, we can see the failure as the number of cycle occurs, the failure stress is significantly lower. Okay. So, this is how the materials are going to behave and fail during a repeated fatigue loading. Okay. Now, we are talking about the damping characteristics. Okay. So, what is damping? So, normally damping is defined is the material's ability to dissipate mechanical energy during dynamic or oscillatory motions. Okay. So, this is the inherent property of energy dissipation. Okay. So, what does damping help in? Damping helps us to reduce vibrations, noise and resonance amplification. Okay. So, if my system, here we can see the classical case of underdamped systems. Okay. So, if the system is overdamped, okay, it will not oscillate, but it will die down. Okay. So, different types of damping mechanism. So, due to microplastic deformation, the damping mechanism can occur. Due to the dislocation motion, the damping mechanism can occur, and due to internal friction, the damping mechanism can occur. Okay. So, these are all combined into one sphere and they are represented as the total damping in a mechanical system. Okay. So, the damping ratio, okay, it is the ratio of the applied damping versus the critical damping. Okay. So, damping is always expressed in terms of the damping ratio, which is the ratio of the present damping over the critical damping. Okay. If the damping ratio is more, it means that the system is going to die down faster and the faster energy loss will occur. Okay. And lower than the critical damping, the system will be oscillating. Okay. And the amount of energy loss will be slower. Okay. So, some of the experimental techniques that we have already seen. Okay. So, split Hopkinson pressure bar, we can use this to characterize the stress strain behavior at higher strain rate. Okay. So, these are used for compression tensile testing, torsion testing, drop weight impact test. Okay. This simulates impact loading. Okay. And these are very simple setups and they are used for panel foams and other composites. Charpy and Izod test, this is used for measuring the impact toughness. Okay. And the total energy absorbed in a system can be measured using this type of configuration. Okay. High speed tensile testing, okay. So, it captures the dynamic tensile behavior, okay. And it requires high speed instrumentation also, such as high speed camera, oscilloscopes, sensors that can acquire readings during a high speed events. Okay. So, high speed accelerometers, strain gauges, etc., and the data acquisition systems are required. Okay. So, these are the different experimental techniques that can be used to measure different types of experimental regimes. Okay. So, dynamic material model. So, here we are defining different types of dynamic material models, which can be used at different applications. The most widely used is the Johnson-Cook Cowper-Simmons model. Both have a basis in the empirical model. Basically, the stress is related with strain and other strain rate parameter using some coefficients A or B depending upon the experimental data. The Zarrilli-Armstrong model, this is normally regarded as a physics based model. Okay. And Johnson-Cook can be used very efficiently for metals at high strain rates. Cowper-Simmons, they are widely used in the crash and impact simulations. Okay. So, split Hopkinson, this is a description of the split Hopkinson pressure bars. Okay. So, in a split Hopkinson pressure bar, okay, this is the setup of a split Hopkinson pressure bar, where it is used to measure the dynamic properties of different types of materials. Okay. Then here the drop weight impact mechanism is shown, where our specimen is kept, okay, and that specimen is subjected to a suddenly falling setup, okay, and the internal behavior of the material can be used. Okay. After that, we can use high speed servo hydraulic testing machines. Okay. So, it has a controlled strain rate deformation. Okay. Okay. So, these are the various testing apparatus. Okay. These are the experimental setups, okay, different types of experimental setups, okay, and have different applications as we have seen earlier. In addition to all these experimental setups, we require strain gauges, we require some sort of digital image correlation setups, okay, and we also require high speed cameras. Okay. So, these are all needed in order to acquire the data that is generated using all these experiments. Okay. So, always the experiments will have two parts, the experimental setup and the data acquisition system. The data acquisition system will have two parts, it will have the sensors and the oscilloscope or the data acquisition system, where the data will be recorded from the sensors. Okay. And since all of these things are dealing with the high strain events, okay, highly dynamic events, okay, like impact events or blast events, okay, the amount of data collected is very large over a very short period of time. Okay. So, that is why the complexity increases and the cost involved with all these sensors, all these data acquisition systems and all this experimental setup is also very large. Okay. And sometimes the testing also has to be conducted at low temperatures, or sometimes it has to be conducted at high temperatures. Okay. So, this again add to the complexity of the system in carrying out experiments for a dynamic setup. So, this is the working principle of a split Hopkinson pressure bars. Okay. So, different components are shown and the total process flow is shown. Okay. So, again the setup of the split Hopkinson bar, we have seen this thing earlier also. A specimen is kept, okay, between two bars and one impactor bar comes and hits the system. Okay. And here the specimen, the response of the specimen is measured and again correlated back to the different known phenomena. Okay. And this is measured using strain gauges. Okay. So, this is how the data collected from the split Hopkinson bar is related back to the desired material properties. Okay. So, these are all the equations showing for the design and calculation of the split Hopkinson bar. Okay. So, now we will look into what is known as the dislocation dynamics. Okay. So, dislocations, what are dislocations? Dislocations are line defects in the crystalline structure that enables plastic deformations. Okay. So, they are mainly of two types. Okay. There are edge dislocations and there are screw dislocations. Okay. So, ductile materials deform plastically via dislocation, glide and climb. Okay. So, dislocation activity under dynamic loading. So, under high state loading rates, so it increase dislocation resulting in generation and velocity. Okay. And there is a limited time for recovery. Okay. So, it leads to the dislocation accumulation. So, this results in the strain hardening, higher flow stress and the rate sensitivity. Okay. And these two types of dislocations are shown here, edge dislocation and the screw dislocations. Okay. So, design of some of the systems. Okay. So, we will be quickly looking into the design of a seismic damping system. Okay. A seismic damping system is a structural mechanism designed to reduce building motion during an earthquake by absorbing and dissipating seismic energy. Okay. So, these are the key aspects of a seismic damper. Okay. Okay. So, these are some of the applications of a seismic damper. These are the viscous damper, tuned mass damper, frictional dampers. Okay. So, different types of dampers are there. They have different mechanisms and different uses in different types of structures. Okay. So, this is the practical application of the energy absorbing devices used as a damping system for a given phenomena, that is earthquake. Okay. So, continuing for that from there, we will be categorizing different materials. Okay. We will be looking into the advantage, disadvantages and the cost effective ratio. Okay. So, steel, we know it has high strength, ductility, readily available and it is reliable. Only drawback is that it is prone to corrosion. Okay. And this has typical application in the crash worthiness applications. Okay. And its normal costing is low. Specific energy absorption, as we have seen earlier, it has moderate, okay, not very large also, not very low also. So, aluminum again wide application in the crashworthiness applications. It has low ductility than steel. It is used in the aerospace and automotive structure. Specific energy absorption moderate to high. Okay. Composites, okay. So, different types of composites are being developed and they have a very high specific energy absorption capacity. Okay. And sometimes the cost of these things also goes very high. Okay. So, after that there comes the hybrid systems. Okay. So, hybrid energy system, what they do is that they combine multiple materials or structural configuration to optimize performance under dynamic loading. Okay. So, what they do is that they use different types of configurations material wise or geometry wise and try to combine the best of the all the worlds, so that the overall energy efficiency is increased. Okay. So, typical hybrid system, metal composite hybrids, foam filled metal tubes, multi-layer laminates and composite metal and sandwich plates. Okay. So, this we have seen their usage, we have seen and their configuration we have already seen. Okay. So, this type of hybrid systems are nowadays greatly used to make a better energy absorbing material. Okay. Again, the mechanism and behavior of the hybrid system. So, typical mechanism is stress strain curve, the high area under the stress strain curve is shown here, and here in this particular hybrid system a front face and a back face sheet is used and the aluminum foam is kept inside as an energy absorbing material. Okay. So, combining the property of the hard plate to distribute the energy over a larger area, and here the aluminum foam is used to absorb the energy. Okay. So, this is how the hybrid system is being designed. Temperature, what does temperature do? So, temperature plays a critical role in the performance of the ductile material under dynamic loading. It significantly affects the material strength, ductility, strain sensitivity and the other failure modes. Okay. So, at a high temperature what is going to happen? So, there will be reduced yield and tensile strength, the ductility and the energy absorption capacity will increase, more uniform distribution deformation and the strain rate localization will take place, okay, and the creep may also influence long duration. At low temperature, yield strength will increase, but the ductility will be reduced. There will be a tendency to brittle to ductile transition, okay. In some metals this will be observed, and there will be a higher tendency towards fracture, okay, and the tendency for the plastic deformation will be reduced, okay. During a impact or a blast event, okay, so the local temperature will rise due to this adiabatic heating, okay, and high strain rate deformation, and this can lead to shear banding and localized failure, okay. So, these are the effect of the temperature on the behavior of the material, okay. So, role of temperature. So, as the temperature increases, okay, we can see a effect on the impact energy, okay. So, there is a transition from the brittle fracture to the ductile fracture behavior, okay. So, microstructural effects. So, the microstructural characteristics of ductile materials such as grain size, shape, crystallographic orientation, the percentage of impurity present, okay. All these things significantly influence their energy absorption capacity under dynamic loading, okay. So, what we can do is that we can manufacture the materials, okay. We can control all these factors, okay, such that we get a tailored, okay, or we get a custom made material which has the desired strength to ductility ratio, okay. So, all these phenomena, grain size, grain shape, orientation, dislocation density, all these things can be controlled and can be used to design a material that is tailor made or custom made to our own requirements. So, this can be done using heat treatment process, okay, and this process can be used to maximize the energy absorption capacity, okay. Residual stresses, okay. So, what are residual stresses? Residual stresses are the internal stresses that remain in a material after it has been subjected to manufacturing or deformation process. So, if we do any sort of deformation to any material, okay, there will be always some residual stresses present, okay, and it will exist even in the absence of any external loading, okay. And in the context of energy absorption system, understanding and controlling the residual stresses is very essential, okay. So, how does it happen? Okay. So, the sources of the residual stresses will be welding and thermal cycles, plastic deformation, machining and cutting, surface treatment and the forming process. So, whenever these things are being done, okay, there will be always a presence of a residual stresses present in the material. Okay. So, measurement techniques. So, how can we measure the residual stresses? We can use destructive testings, okay. We can drill some holes, okay. We can remove the layers, or we can use some NDT techniques also, okay. So, we can use X-ray diffraction, neutron diffraction, and we can use some sort of ultrasonic method also to measure the residual stresses, okay. So, what we can use this thing, okay, while designing an energy absorption system. So, what we can do is that we can design with compressive surface stresses to delay the crack propagation. We can use controlled heat treatment to reduce the residual tensile zones, and we can implement the symmetrical fabrication and balance cooling paths to minimize the stress gradients. Okay. So, all these methods we can use in order to control the residual stresses, so that our energy absorption systems behave in a proper way. Okay. So, rate dependent damage models. Okay. So, the development of the damage model using the rate dependency. So, damage evolution in ductile material is rate dependent. Okay. So, we have already established that the rate dependency follows a crucial rule in all the materials. Okay. So, at higher strain rate, okay, the damage growth can be accelerated and the failure mode can be altered. Okay. So, what we can do is that we can develop the coupled constitutive damage models. Okay. So, what that will do is that it will integrate the stress strain behavior. Okay. So, this is the stress strain behavior, okay, and it will be coupled with the propagation of the internal damage. Okay. So, due to various factors like porosity, micro crack density, impurity, voids, okay, and any other mechanism, okay, the formation of this damage, okay, or this factor D, okay, this both can be combined to develop a coupled constitutive models, okay, which takes into account the mechanical behavior as well as the propagation of damage in the material model also. Okay. So, D is defined as the damage variable, okay. 0 means undamaged and 1 means fully damaged, okay. And this damage rate will also have a strain rate sensitivity. Okay. So, in this way we can develop a holistic model which takes into account the mechanical properties also as well as the propagation of the damage in the material also. Okay. So, this will give rise to a properly developed material model that can be used in the dynamic analysis, okay. And it is taking into account the effect of the temperature, it is taking into account effect of the strain rate, it is taking into account the microstructural damage mechanism also. Okay. So, damage evolution characteristics. Okay. So, using this developed damage models. Okay. So, if this is properly accounted for, it will reduce the time for stress redistribution, it will enhance the micro void growth and it will increase the thermal softening phase also. Okay. So, if the damage evolution characteristics are properly accounted, okay, then during high strain rate this phenomena can be accurately predicted. Okay. Then the thermal mechanical coupling, okay, the coupling of the stress strain behavior, damage propagation and the influence of the thermal properties under this behavior, okay, that also becomes critical during the high strain rate phenomena. Okay. So, this can be applied into high speed impact, crash simulations and explosion simulations. Okay. And here we can see an application of this developed model used in the finite element simulation. Okay. So, these things later on when we are dealing with the finite element model, we will use this type of simulations and we will try to see how our this developed models, okay, validate with the actual experimental phenomena. Okay. So, we will try to have our hands on experience with the finite element model and those things we will try to validate with the available experimental data. Okay. Moving ahead. So, optimization techniques. So, the dynamic performance of the ductile structures, okay, they can be optimized using the advanced optimization methods. So, one crash worthiness examples we have already seen in our previous lecture, where we use the surface response method to optimize the properties of our developed energy absorption device. Okay. Other techniques are topology optimization, okay, genetic algorithm optimizations and design of experiments. Okay. This in turn combined with the response surface methodology can be also used as a powerful tool in optimizing the behavior of the different types of energy absorbing materials. Okay. Okay. So, use of optimization in dynamics. So, it will improve the energy absorption capacity, it will improve the failure resistance, it will reduce the mass, okay, and thereby increasing the impact performance and the tailor made geometries, okay, like with the advent of the 3D printing, okay, different types of tailor made geometries can be used for the localized strain rate deformation. So, we have already seen an example where we have used the response design of experiment and response surface methodology in designing an energy absorbing barrier. Okay. So, similar things can be used for the design of crash box, armor panels and other materials to protect from any type of dynamic event such as impact and blast. Okay. So, here we can see the deformation process of the lattice structure. So, with the advent of the 3D printing, this has become very common nowadays, okay. And this is being optimized using the criteria of the von Mises stresses. Okay. So, here the von Mises stresses are used as a parameter for optimization. So, in order to quantify the energy absorption characteristics, okay, some metrics are used. So, one of the metric is the total energy absorbed, okay, mean crush force. Okay. So, the total energy is nothing but the area under the load displacement curve, mean crush force, that is the average force during crushing process. Okay. So, total energy absorbed divided by the maximum displacement will give the mean crush force and the crush force efficiency. Okay. So, this is the ratio of the mean force to the peak force. Okay. So, this type of matrices can be used to quantify the energy absorbing materials. Okay. So, this type of energy absorption matrix, they are help to assess the safety and durability of the structure under impact or crash. They helps us in comparing the different types of optimized material configuration, and they are used in different examples. Okay. So, these are used to compare the energy absorption capacity, establish a stable crushing behavior and establish a possible progressive failure mechanism, okay, and stop the catastrophic breakage of the system. Okay. So, in additive manufacturing process is also used to develop different types of energy absorbing materials. Okay. So, what is the advantage? Okay. So, the core advantage of the additive manufacturing process is that there is a freedom in the geometry. Okay. So, using the traditional machining, okay, topology is cannot be controlled, but herewise there is a freedom in the geometry. Okay. The material efficiency is achieved here, and there are tailored deformation modes. Okay. So, we can predict or we can achieve a progressive stable failure zone. Okay. So, common additive manufacturing metals for energy absorbing structures, okay, like titanium alloys can be used, aluminum alloys can be used, or other types of materials like stainless steel or Inconel can also be used. Okay. So, these are the process of designing for the internal geometry. So, comparing the additive manufacturing process. Okay. So, these are the features of the different types of process like selective laser melting and electron beam melting. Okay. So, these are the some of the processes that can be used in order to achieve a higher material or higher efficiency of the material. Okay. So, all these things can be used to have an uncertainty and the probabilistic modeling. Okay. So, what happens? Each of the design methodology, okay, they have two parts. One is the capacity of the system and other is the demand imposed by the external forces. Okay. So, what we are always trying to achieve? We are trying to achieve a reliable system, okay, meaning we are trying to minimize the probability of the failure of the system. Okay. We are always trying to achieve a reliable system. Okay. So, what we can do is that we can always aim for a reliability based design, okay, where our goal is to achieve or minimize the probability of the failure of this system. Okay. And that takes into account all the uncertainty in the capacity of the energy absorbing process and all the uncertainty in the external process, be it impact, be it blast or any other dynamic event. Okay. So, if we can account for the uncertainty in both the capacity regime and in terms of the demand regime, we can achieve a reliable system. Okay. So, what reliable system will give us? So, it will incorporate the safety margins required and the failure probability. Okay. So, we will have an estimate of the failure probability of this system, and we can then again put the optimization process also to achieve or to maximize the reliability of the system. So, it will be a robust design, and the failure modes also we can control, okay, by selecting our own limit state function. So, we can design for ductile failure mode, we can design for brittle failure mode and achieve the required reliability. Okay. So, we can incorporate all the uncertainty in the system to achieve a reliability based design. That is the main goal that is being tried nowadays. Okay. So, we can incorporate all the knowledge which whatever we have achieved for the uncertainty modeling and put this thing into use. Okay. So, as the course progresses, we will also try to have an example of a reliability based design of an energy absorption systems, and see how efficiently we are trying to achieve the optimization process and achieve a greater or reduce the probability of failure of the system. Okay. So, I end my class here. Thank you.